with this arrangement, I think the simultaneous inputs problem was solved. Then hereafter, there is no problem with that. Then actually that the things we have changed with this modification is that actually with the timeline, we have this before applying the clock and after applying the clock, likewise that we have this present and next state change. And previously we had that present state, next state, and previous state like that. Okay, this way. But after that, with this new addition, after adding this clock input, now we have changed all these flip-flops. Hereafter that any flip-flop is having clock input, then this notation will be there. The meaning is n+1 qn means that qn means that before applying the clock pulse, and qn+1 means after applying the clock pulse. Actually, here you may realize that at the moment, until you apply a clock pulse, the flip-flop doesn't know the values has been given to its inputs. For example, in this case, you can set values to this R and S inputs, but until you give this clock input 0 to 1 transition, okay, then these values will not be transferred to the inside of the flip. Then, as a result, flip-flop doesn't know there are inputs at the input level, and it doesn't change its output. Okay, then as a summary, actually that any flip-flop having this clock input, it doesn't matter it's JK, D type, or whatever the flip-flop. Okay, then if the flip-flop is having this clock input, okay, how can we give inputs to input values to a flip-flop? First step, set values to inputs. In this case, whatever the flip-flop, it doesn't matter, it's JK or whatever the thing. For the moment, shall we draw JK? Now, this is the first step. And here, we set this value here 1, logic 0. This is our flip-flop. And this is clock input. In first stage, we set these values. Okay. During this time, then after that, we say that this clock input may be 0. Okay. After the second step, issue a clock pulse to clock input. This clock input means CLK inputs. Okay. This is the second step. Then here, you have to issue this clock input to this. This is the second step. If you complete these two steps, then only you can give values to flip-flops, and then only flip-flops can change the inputs accordingly. It's something like that. I'm always taking this example that it's something like that. You want to give some kind of the parcel or whatever the thing to your neighbors. How can you go do that one? You can take that parcel and place that parcel at the doorstep of your neighbor, and you come back. But do they know that you have given some kind of parcel, you have placed some kind of parcel at their doorstep, and they are supposed to take those things inside? No, they didn't know. Then what you have to do is you can go there and place the parcel at the doorstep, then knock the door. The placing the parcel at the doorstep means the step one, set values at inputs. Okay. The knocking the door is giving the clock pulse. Then giving this clock pulse, you are triggering the flip-flop. Okay. Then when you trigger the flip-flop is to trigger the flip-flop, you have to give a clock pulse. Then only you can inform the flip-flop. There are certain values at JKO, RSO, DV inputs. Please take those things and give the outputs. To do that, you have to give this clock input. Then you have to remember this one. Is it okay? Shall we go to the next section? If you understood all these things. Any question? Okay, then if you don't have any question, then we can move on to the next section. It's actually flip-flop applications. Okay. Okay. Then today our topic is flip-flop applications. Okay. But we have so many applications with flip-flops, but we are not going to discuss all these things here. We'll discuss one important one actually important, and it may be useful, and it may be sometimes having some kind of beautiful nature, beautiful operation. Then, do you remember that the JK flip-flop truth table? This is our JK flip-flop. And truth table of this one is this is Qn 0 1 Qn bar. You may remember that to trigger a flip-flop, what we have to do, we have to give a clock path to this clock in. Okay. If I ask you a question, oh, this is our clock pulse. Actually, this clock pulse mean this is the 0 level, and this is logic 1 level. In practical case, this is 5 volts, some kind of positive voltage, and this is 0 volts. Now you can see. Okay, sorry for that. Now this is flip-flop applications. Now I have taken this JK flip-flop and I have drawn the JK flip-flop truth table also. I'm asking the question that when you give this clock input to this type of flip-flops, offsetting whatever input values, the flip-flop will change its output value. My question, and this is the clock input. This clock input is something like that. It's having this logic 0 level. Here, this is logic 0. After that, this is the 0 to 1 transition edge, and then it will be there at 0 level for certain time. After that, it will be coming back to logic 0 level. Then from this logic 1 to 0, another transition time may be there. Okay, this is how it goes. Okay, anyway, if I ask a question that now you can see here, and in this clock pulse, we have clearly 4 different parts. 4 different parts means I can name this one. This one is, we say this is negative level. This is negative level. And this one, this is rising edge. This is, we can say this is positive level. And this one, this is falling edge. This is rising edge, falling edge. Now you can see that with single clock pulse, we have 4 different parts. Can you say me, and which part of this clock pulse is responsible to trigger the flip-flop? We want to trigger the flip-flop. After giving the input values, we want to trigger the flip-flop. Then only you can change the output value. Then only flip-flop can take input values and do the changes to the output. That is, to that we are giving a clock pulse that is triggering. Okay, with this triggering pulse, actually the pulse is having 4 different parts. Which part is responsible to do the change? Yes, some of you have mentioned it's a positive level. Exactly correct. That's what, that if you consider the RS latch, then after adding certain one, after adding certain circuit part there, then we have converted that into JK clocked RS flip flop. They are definitely we have changed our output level in the positive level of the clock pulse. But anyway, the manufacturers, they have developed the different type of flip flops. Okay, different type of flip flops having different triggering parts of the clock pulse. Okay, then we say this is triggering methods of the triggering methods of a flip flop. So here this is our clock pulse. And manufacturers have developed their flip flops to trigger in this negative level or this positive level. If you do like that, then we call this flip flop is, this is negative level triggered flip flop. And the symbol of this flip flop is, you have to remember this one very carefully. JK. This is negative level. Okay. Because of that, this clock input is shown like this. Okay. Next one is, this is positive level. Positive level triggered flip-flop. For such flip-flops, this is the way the clock input has gone. Okay. But if flip-flop was triggered in here or here, we say this is rising edge. Triggered flip-flop. And symbol for this rising edge triggered flip-flop is JK. This way. And this one, falling edge triggered flip-flop. You can see these are edge triggered flip-flops. And they are level triggered flip-flops. Here the important part is this one. This is clock. Sun and this. Then when you buy a flip-flop from the market, then you can refer the data sheet Then based on your data sheet, you can determine and what type of flip-flop you have taken. And according to the data sheet, then considering this symbol, you will identify that whatever the edge flip-flop will use to trigger the flip-flop. Okay. Okay, if you are okay with that, then considering all this knowledge you have gathered here, now tell me that what happens if you have this type of arrangement. You have this JK flip-flop, and the responsible edge of the flip-flop to change this one is falling edge, and the falling edge flip-flop will be triggered. Initially assume that this output is at 0. Okay, then here I take this two wires and put permanent 1-1 to J and K. And to this one, I give clock pass. Okay. Then to see what happens there, then you should know the JK flip-flop truth table. 0 0 QN 0 1 0 1 0 1 then 1 1. 1 1 means QN bar. Okay. Then giving permanent 1 1 to this JK flip-flop means actually we are using this last combination only. Name for this last combination is actually the toggle mode. We will see that why they have given this name toggle. Okay. Now flip-flop is in the last stage. That means we have given 1 1 to its input. So during this time, after setting this 1 1 to this J and K inputs, now you can issue a clock pulse. Okay. Now you can issue a clock pulse to the clock input. Then assuming that initially Q was 0, now what is the Q value? Now the present Q value should be inverted value of previous output. Okay, then find the previous output, invert it, and then say your answer. Okay, then shall we take this output as A? Okay, then I'll draw a diagram showing this clock input. This type of input we are giving to this clock input while we are keeping JK at 1. Okay, this is clock in. Okay, now we want to draw A. Initially A was 0, and after that we have to determine the value A based on the information and based on the knowledge we have gathered from this truth table and with this working experience with this flip-flop. Okay, take a couple of seconds and think about that one. And can you draw the output of A? Sorry, I was muted. First thing, you have determined what type of triggering method this flip-flop is having. After identify the triggering method of this flip-flop, then you can identify the responsible part of the clock pulse to change the output, to trigger the flip. Okay, what type of flip-flop is this? What is the triggering method of this one? It is falling edge trigger. Okay, then if it is falling edge triggered, then falling edge of this flip-flop, falling edge of this pulse is responsible to trigger the flip-flop. At these falling edges, flip-flop will be triggered. Initially, forget about this pulse train. Assume that you have only single pulse. Assume that then initially output A is at 0. Now it can remain there until it receives a clock pulse. But here, excuse me for a couple of minutes. Oh, Okay, here then this A remains at 0 until it receives this falling edge. At the falling edge, what is the next output value? It's Qn bar. Qn means previous one. It should be inverted. Then inverted means it should go to 1. It should go to 1 and remains there. Okay. When it is there, it receives the second clock pulse. Okay. It receives the second clock pulse, but it does not change until it receives the falling edge. At the falling edge, it is coming, it will be inverted. It means it's coming back to 0 and remains there. And during that time, it receives the third clock pulse. At the falling edge of third clock pulse, it will be changed and goes like that. Is it okay? Dilhara, that you are asking the question, the difference between the diagrams of negative level triggered and falling edge triggered. Okay. Here, the negative level triggered means when the flip-flop, when the clock pulse is at 0 level, the flip-flop will be triggered. Okay. Then here we have small circle at the clock in. Okay. When it comes to the falling edge, you can see here, in addition to this small 0, so small circle, inside that we have a small triangle. Something like that. Inside we have small triangle and small circle. This is clock. As I drawn here. Okay, then if you're okay with this, then what will happen then? Actually, at each and every clock input, the flip-flop output has been changed. How? It has been changed 0 to 1, 1 to 0, 0 to 1, 1 to 0, like that. It has been toggled. That's why we say this toggle output. Okay, it's going in between 1 and 0, 1 and 0, 1 and 0, like that. Okay. Then actually, when we combine this one, then we have, generally we have another type of flip-flop also. And it's not a new type of flip-flop. But when you have this flip-flop, and we say this is T. T means toggle type. When you combine this JK inputs together, and if you make a new type of flip-flop, it's here we have T. Now this is the clock input. Q, Q. It's common for any kind of triggering method, but here I have drawn this one for the falling edge trigger flip flop. That's why I use it. This one is T type flip flop. T type flip flop means toggle type flip flop, but there is no difference between J and K here. Actually, the difference between this J and K and T, this one, inside that we have combined JK together, nothing else. Okay. Okay, now if you are okay with this one, shall we try to understand operation of this circuit? Here, actually, that we have this toggle type flip flop. We have all these flip flops that we have combined JK and given 1 1 permanently to this J and K inputs. Okay. Shall we try to understand that the operation of this one? Actually, if you know when you give this 1 1 to this J and K flip flop, so you know that how they are behaving. Okay. Here, now we are giving this clock pulse to this first flip flop. We take this first flip flop output as A, and we give this first flip flop output to the second flip-flop clock input. And the second flip-flop output is B. And we are taking B to the third flip-flop clock input. And third flip-flop output is C. And following the same pattern, we are giving this one to the fourth flip-flop clock input. And the fourth output is D. Okay, then as we discussed earlier case, this time also we are giving this clock input pulse train to this clock input, something like this. And you know, you have, I think you have noticed that all the flip-flops are falling edge triggered flip-flop. Therefore, this falling edge of this clock pulse train, they are responsible to change flip-flop A out. This one. Okay. Then shall we draw output A according to this one? A. And you can see that here. Okay. Shall we draw A by considering this clock input pulse train? Okay. Then initially we can assume initially A is at 0. Then when A is at 0, it receives, flip-flop A receives clock input. Then, but it's a falling edge triggered flip-flop. Because of that, it remains, it remains at 0 until it finds this falling edge. At the falling edge, it will be changed to logic 1, and it will be there until it receives the second clock input falling edge. At the second falling edge, it will be changed to again 0 and remains there until for third clock pulse falling edge. And after that, it's going up and coming back Likewise, it goes like this. Okay. Okay, now we can draw B by considering A. Why? Because to draw, we have to consider its clock input. Its clock input is A. We have connected A to the clock input of the second flip-flop B. Okay. Then we can draw this B output considering A output. Okay. There are also the falling edges of this waveform A. These pulses falling edges are responsible to change the output B. Yes, all the time we assume A, B, C, D, all these outputs are at initially they are at 0. Okay, considering that, then let's draw this B. B will be there at logic 0 until it receives the clock pulse falling edge. Here it receives it, then it will be changed to logic 1, and it will be there until it receives the falling edge of the second clock pulse. There it will be changed back to 0, and it's going like this. Okay. Then we can draw C by considering B and D also. Okay, how can we draw C? By considering B, especially falling edges of this B. At these falling edges, C will be changed. And like that, now C has received the first clock pulse, but it waits until it receives the falling edge. At the falling edge, it will be changed and remaining there for the second falling edge. At the second falling edge, it will be coming down and going up at the third falling edge. Now we can draw D by considering C. Is it okay? Is it okay? Okay. If you're okay with this diagrams, okay, shall we put values of this waveforms? Actually, these are timing diagrams. Okay, we call these are timing diagrams of output A, B, C, D. Okay, shall we put values there? Here A0, B0, C0, D0. Then here A1, B0, C0, D0. Here A0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 1. Okay, if I write those values a table. For example, then if you consider these values, then first, what is this? B0, C0, B0, AC. Second one, 0, 0, 0, 1. Third one, 0, 0, 1, 0. If you write these things in a table like this, initial one is 0, 0, 0. The second one, 0, 0, 0, 1. 0, 0, 1, 0. 0, 0, 1, 1. Then 0, 1, 0, 0. 0, 1, 0, 1. 0, 1, 1, 0. 0, 1, 1, 1. Okay. After that, we have 1, 0, 0, 0. And 1, 0, 0, 1. Okay. Then 1, 0, 0, 1. Then 0, 1, 0, 1. 1, 1, 0, 1. 0, 0, 1, 1. Okay. That's how from the diagram we have received. Okay. Now, can you see this? Can you identify any pattern with these numbers, with these values? What about if you consider the decimal equivalent of this number? This is 0. And this is 1. This is 2, 3, 4, 5, 6, 7, 8, 9. And this is 10, 11, 12. Okay. But actually it will continue up to this value also. Okay. Then 13, 14, 15. After coming to 1, 1, 1, 1, what will happen? Here, you can see here, after coming to 1, 1, 1, again starting 0, 0, 0, 1, 1, 0, 1. Again 0, 0, 0, 1, 1, 0. For the third bit also, after coming to 1, 1, 1, 3, 1, starting from again 3 zeros to going up to 1, 1, 1. The same thing will happen at the last also. Yeah, after coming to this one, it will go back to the first one. It's coming down like this. Okay. And going back to, after coming to this 1, 1, 1, 1. Okay. Then what is this pattern? What type of action you can see? What type of pattern you can see at the output? You can see this increase in numbers 0, 1, 2, 3, 4, 5, 6, 7, 8 like that. What is this action? It's counting. It's a counter. It's a kind of counter. It is counting what? Actually, all the incoming clock pulses, it's counting. After receiving one clock pulse, it says it's 1. After receiving 2 clock pulses. It says it's 2. After receiving 3, it says it's 3. Okay. Likewise, it goes. Therefore, this is a count. Okay. What type of counting action we can see here? 0, 1, 2, 3, 4, 5, 6, 7, 8, like that. What type of counting action? Actually, it's a up count. But what are the numbers we can see? What are the numbers we can see? It's 0, 0, 0, 0, 0, 0, 0, 1. All these numbers are binary. Because of that, it's binary up count. But what is the specialty of this count? What is the capacity of this count? How many flip-flops have we used here? Can't we use 2 flip-flops? Can't we use 3 flip-flops? Can't we use more than 4? How can we specifically mention we have 4 flip-flops? There's a relationship. And how many output lines are here? 4. It's DCBA. 4 output lines are there. With that, what type of number we can see? 0, 0, 0, 0 to 1, 1, 1, 1. Then what is the number here? It's 4-bit number. Because of that, this is 4-bit binary up count. This name suggests us is 4-bit binary up count. Counter, it's okay. It's fine. When you say 4-bit, there should be a then 3-bit count. There should be a 5-bit count. There should be a 64-bit count. Is it possible? Is it possible to make 2-bit count? Sorry. What do you think? Is it possible to make 2-bit count? Okay, forget about that question. With this 4-bit binary counter, with this 4-bit binary counter, what is the minimum value? What is the maximum value? Minimum value is 0, 0, 0, 0. Maximum value 1, 1, 1, 1. 0 to 15. If it is 3-bit count, what is the minimum value? 3 zeros. Maximum value 3 ones. This is 0. This is 7. 0 to 15. This is 0 to 7. When you consider 0 to 7, altogether including 0 and 7, we have 8 stages. When you consider 4-bit count, including 0 and 15 altogether, we have 16 stages, 16 different numbers, 16 different patterns. When you say 2-bit count, minimum is 0, 0, maximum is 1, 1. 0 to 3, including 0, 3, all 4 stages are there. What about that if you have 5-bit? It's 0, 0, 0, 0, 0 to 1, 1, 1, 1. Then this is 0 to, what's the number here? It should be 31. 0 to 31. Is it possible to expand this one? Is it possible to reduce this one to 2-bit, 3-bit like that? Yes, it's possible. Have you identified there is a pattern here? When you make this circuit, have you identified there is a pattern? Okay, then you can take a similar type of flip-flop. In this case, falling edge triggered flip-flop, you can take, and after that you can combine J and K inputs and put it to one logic 1 and take the output from the Q output and take the clock input from the previous stage. In this case, if you are going to connect flip-flop here, you can take the fourth output line and connect to the fifth clock pin. And if you are going to connect 6th one, take the 5th output and connect it to the 6th flip-flop clock in. Is it okay? Likewise, you can continue. Then increasing this one to 4 bit, there is no problem. Decreasing this one to 3 bit, there will not be a problem. Okay, you can do it. But what do we expect that after changing the bit capacity? Considering the bit capacity, it says us the minimum and maximum, the range of the count. It specifies the range. Okay. But actually, when you see this one, when you come to this timing diagrams, okay, when you come to this timing diagrams, if I say this clock input is, the frequency of this clock input is F, what is the relationship between this F and A? What is the frequency of A? Frequency of A equals F by 2. Frequency of B equals F by 4. Frequency of C, this one. Okay. For this C, 1 pulse, we have taken 4 clock pulses. It means by, this is original one, we have divided by 8. When you consider frequency of D, then it's divided by 16. Then instead of saying this is 4-bit counter, instead of this 4-bit, you can say this is divide by 16 binary up count. Why? It's 4-bit. 4-bit means divide by 16. Why? Because this D output waveform, when you consider this D output waveform, the relationship between the original frequency and the D frequency of D output is a original one. When you divide it by 16, it equals to D. Okay. Then in addition to that, saying this is counter, you can say these are frequency dividers. These are frequency dividers. How can we divide frequency? If it is 2-bit counter, you can say this is divide by 4 count. You can divide original frequency by 4 when you use 2-bit count. When you use 3-bit counter, it's coming up to ABC. Then instead of saying it's a 3-bit counter, you can say, okay, instead of saying this is a 3-bit counter, you can say it's a divide by 8 count. Okay, it's a divide by 8 count. You can say like that. Okay, instead of saying that it's a divide 4-bit counter, you can say it's a divide by 16 count. Okay, this is another name for this type of counters. Okay. Yes, then if it is 5-bit counter, then you can say it's a divide by 32 count. Okay, this is another name for this one. Then equally you can say it's a 4-bit divide by 16 counter. But here I say the binary counter is important. Then another one is here. This is up count. If it is up counter, definitely there should be down counters. But so far I have mentioned many things to you. Is it okay with you? All these things up to this point, is it okay with you? What are the things I have mentioned? I have mentioned the bit capacity of these counters. Depending on the bit capacity, the counting range is changed. So example, if it is a 4-bit counter, the range is 0 to 15. Altogether, we have 16 stages. Because of these 16 stages, we can say this is a divide by 16 count, or divide by 16 frequency divide. We can say like that also. You can consider this as a counter or as a frequency divide. When you say frequency divided, the division number, you have to consider the bit capacity. If it is a 3-bit counter, you can say it's a divide by 8 frequency divide, or maybe divide by 8 binary count, or maybe 3-bit binary count. Like that you can mention. And you can see these timing diagrams also. When you look at these timing diagrams, it's clear that all the time the next output waveform, will be half of the previous wave, the input clock frequency. That's clear. Okay. Other one, this bit pattern. It's always going between 0, 0 to the minimum number to maximum number, if it is the up count. Okay. The other thing we have discussed, we can change the bit capacity of this one, and we can expand this one up to, theoretically, you can expand this one up to infinite number of flip-flops. Theoretically, it's possible, but practically it's not. Anyway, that we can say it's a 5-bit counter, 16-bit counter, 32-bit counter, 64-bit counter, like that. You can expand this one. Okay. Then other thing, I have mentioned this is up count. Okay, if this one is up count, how can we make down counters? Oh, Didula, that you are asking that how can we find whether counter is up or down? But by observing this bit pattern, by observing this, its output values. It is 0, 0, 0. Initially, we had this one. The second one, 0, 0, 1, 0, 0, 1, 0. Then it's a 2, 0, 0, 1, 1. It's 3. Then you can see the output pattern 0, 1, 2, 3, 4, 5. Then it's up count. Is it clear? No. If we give the input as that one answer I have received, if we give the input as 0, it will be down count. But we can't receive this action, this toggling action, unless we connect this flip-flop to 1, 1 permanent. Because when you consider the JK flip-flop truth table, this 1, 1 combination gives only this toggling action. If you change this input to 0, 0, it will do nothing. Okay. But what about this one? Okay. What about that if you take this output from this Q bus? This is A bar. This is B bar. This is C bar. And this is D bar. Okay. Look at the values. If DCBA is this, shall we write D bar, C bar, B bar, A bar? Then this should be 1, 1, 1, 1 and 1, 1, 1, 0. And this is 1, 1, 0, 1. What is this? This is 15. This is 14. This is 13. It goes like this. Then without doing any change, if you take output from Q bars, then while that A, B, C, D is giving up count, definitely A bar, B bar, C bar, D bar giving down count. Without doing any change, you can take down counting action from A bar, B bar, C bar, D. I think last week, one of your friends asked me that why we have taken that DCBA order, the reverse order for the DC to 7 segment decode, because of this reason. Here A, B, C, D, the A is having the least number. B, C, D, D is the largest number. That's why we change this DCBA order in the BC to 7 segment decode. Now you can connect this counter directly to your BC to 7 segment decode. Why? D is the highest number. D is the most significant digit of the number. And A is the least significant digit of the number. Okay. Okay, one thing to take down counters. Okay, then many things, and you can do these changes. Okay. Changes you can try. If you are okay with this, all these things, these changes you can try. Okay. And that for down counting, without doing any change, to the circuit, take B bar, C bar, B bar, and A bar. Other thing you can try, change the type of flip-flop. That means here we have used, what we have used? We have used falling edge trigger. Falling edge trigger flip-flop we have used. Okay, you can try at least, but don't try to draw diagrams using the level triggered flip-flop, the positive level triggered and negative level triggered. Don't do that one. Okay, you have my word that will not come to the examination. Okay, try this one, the rising edge triggered flip-flop. Rising edge triggered flip-flop. Now, already we have drawn this one for falling edge triggered flip-flop, but you can change this flip-flop to rising edge trigger. Then draw the timing diagrams and see what type of counting action is there. That's exercise for you before your examination. Okay, then you can see the counting action will be changed. Other thing, the third step you can try, change clock feeding method. What does it mean? In this case, you have given A to clock. B to clock like that. But change this one, A bar to clock. B bar to clock like this. Here, we have given clock input from taking it A. Then now you have taken clock input from A and give it to the second stage flip-flop clock input. Now change that one. Take the clock input from A bar and give it to clock input. From B bar to clock, C bar to clock. Like that, change that. Then when you do all these things, you have four options. First one, falling edge triggered flip-flop, taking clock from this one, this combination. Falling edge triggered flip-flop and clock feeding method is A to clock. Then second one, change the rising edge triggered flip-flop, clock feeding method is A to clock. And this both falling edge, rising edge triggered flip-flop you can use and change clock feeding method A bar to clock. Then you have four options. If you have drawn all four options before you come to the examination, nothing else you will have other than that. When you have covered all four options, then don't worry about the examination, because anyway, that definitely one of the question is coming from this section. Today is our last day for this digital electronics section. Actually, we have taken one lecture additionally also. According to the schedule that we have to cover up this one within 6 lectures, but I have taken 7 because of this power issues and all these things. I think some of the time that we had, we did not have 2 hours maximum the entire period. Because of that, we have to use the 7th day also. Today we are going to finish this one section. This is the last thing I have to discuss with you. Definitely because of that, this is the last section and the very important one. Definitely one question you can check the previous papers also. And definitely one of the question is coming from this section. Therefore, my the personal advice is that before you come to the examination, if you try all these 4 methods, then there will not be any other method other than these 4. Okay. Okay. Any question that before we finish the section, and until that, so far starting from the flip flops and coming to the different type of flip flops, and after the flip flop applications, and we discuss different triggering methods of the flip flops also, and after that this count. Any question regarding all these sections? Anything? Any question? Okay, anything, any question? I thought that you have many questions. Okay, then you can check the past papers and everything, and maybe we'll have the tutorial session also. During the tutorial time, we can ask any question. And from next week onwards, that we are starting this analog electronics section. Okay, then if you don't have any question, then we can finish the session. And thank you very much for your participation. Thank you very much for your time. And we will meet next week, usual time. And in the meantime, that I'll upload these things to the internet and send the links to you. I think in any case, that if you want to contact me, that this is my number. For any kind of inquiry, but please let me know that you are a student from ICAM. Otherwise, that if I'm in the meeting, that I will not pick up the phone. Please send me a SMS before you contact me. Sorry. Okay, then thank you very much and have a nice week. and we'll meet next Monday. Until that, be safe and take care of yourself. Thank you very much. Shall we stop?